Okay, so let's solve another problem, this time 6.14 exercise. We have this circuit here, and now if we look at the BJT in this circuit, it's a PNP, right? Because the arrow now is pointing inside the BJT, so it basically means that our emitter, we have our emitter here. So this is the emitter current, IE. Do it again, IE here. Then we have IB here and IC here. So from this problem we know that the voltage at the base, so the potential at the base, right, is 1 volt. So it's 1 volt, 1 volts. And the potential at the emitter, right, is 1.7. And we need to define alpha, the common base current gain, and beta, the common emitter current gain. And also define what's the value of VC, the voltage, the potential at the collector of the BJT. So those are the unknowns. Okay. Now, again, we can assume that the BJT is operating in the active mode region, right? So to verify that, because it's a PNP transistor, we must have VEB equals to 0.7. So VEB is equals to VE minus VB, which gives us 1.7 minus 1 equals to 0.7. So for our first condition, VEB equals 0.7, that's okay. So we can proceed with the active mode equations that we have. Okay. Now we can calculate one of the currents, so we can start with the collector current. Let me see. We can start with the emitter current. So if we look at this circuit, basically we know this potential VE, we know this potential here plus 10, so we know the voltage across this 5K resistor, right? So this voltage plus minus V here, 5K, is equals to that 10 volts minus VE, and that's equals to the current at the emitter times those 5K ohms. So this one here, VE, we know from the statement up here, right? We can define IE. So if we isolate IE, the emitter current is equals to 10 minus the voltage at the emitter, which is 1.7, divided by 5K. Oops. Just rewrite this stuff here. So IE IE equals to that 10 minus 1.7 divided by 5k, and that's equals to 1.66 milliamps. So that's the current at the emitter. Okay, now if we look at this circuit again, basically the current that's flowing here at the base, right, so this IB here is the same current that's flowing through this 100k ohm resistor, right? And since we know VB, the potential here, and we know that here we have 0 because this terminal of the resistor is grounded, we can also calculate this potential difference here that we can call V100K. And this V100K is equal to VB minus 0, which is the same as the base current times the 100k ohm resistor. And from the statement of the problem, we know that VB is equals to 1 volt. So the current at the base, IB, is equals to this 1 volts divided by 100k ohm, and that's equals to 10 microamps. So this is the current at the base. Now, because we know the current at the we don't know the current at the collector yet, so we can calculate the current at the collector. And the current at the collector is just IC is just IE minus IB, which is the same as 1.66 milliamps minus those 10 microamps. IC is equals to 1.65 milliamps. Now, because we are assuming active mode operation of the BJT, there's a relationship between the collector current and the base current. So the collector current is the same as common emitter current gain times the base current. If we manipulate this equation here, we can isolate beta as the ratio of the collector current divided by the base current. And because we know IC and IB, we can calculate beta equals to this ratio, 1.65 milli divided by 10 micro. And this gives us 165 for the current gain. So we find out the value of beta. Now there's another equation that we can use to calculate alpha. So alpha, the common base current gain, is equals to beta divided by beta plus 1. So remember that alpha is always less than 1, right? Because the numerator here is always less than the denominator down here. Right? So this is plus sign. And in our case, this is equals to 165 divided by 166. This gives us an alpha that's approximately 0.994. And now we still need to define the voltage at the collector, right? So this voltage here. Now we know the current at the collector This IC here we know, and we know this potential here. So we just applied the same condition. Basically, we know this potential here, right? V5K, and this V5K here is the same as VC minus those minus 10 volts, and that should be equals to IC times the collector resistance, which is 5K. So from this equation here we can isolate VC as IC times 5K minus 10. This gives us a VC, so if we substitute the value of IC here, gives us a value of VC that's minus 1.75 volts. And we can again verify the active mode operation, right, by verifying the voltage VCB. But now because it's a PNP transistor, that relationship VCB should be less than 0.4 volts. So VC, we know it's minus 1.75, and VB we know from the statement of the problem that's 1 volt, right? So it's minus 1V, which is equals to minus 2.75 volts. And this 2.75 minus 2.75 is indeed less than 0.4 volts. So this agrees with our assumption of active mode region. So the values of VC, the value of VC is minus 1.75, alpha is 0.94, and the beta, the common emitter current gain, is 165.